So let's just go ahead and start off with your background. Maybe tell us a little bit about yourself.
Yeah, sure. I'm Devvrit. I am in my fifth year of PhD right now at UT Austin. I work with Professor in the GTLM. I'm mainly interested in things like large scale machine learning. Recently, have been focusing more on, say, scalability or efficiency of different algorithms. And before I started my PhD, I did my master's at UT as well. And even before that, I was for like wonderful 4 years. I spent at BITS Pilani Goa campus during my undergrad.
Mhm. Awesome. So maybe tell us a little bit about your experience in undergrad, like sort of like what motivated you to get a PhD. What was your sort of interest in research, and how did that sort of develop over time?
Yeah, that's an interesting question. So, to begin with, like when I was in my first or second year at my undergrad, I started liking the CS courses. The first time I did any kind of coding was in my first year, when there was like this generic computer science course. So, Let Us See was like the book that was referred to, the like what most of the people use in their undergrad back in India, and it was fun. I liked like solving puzzles, solving those coding problems. That's how I got interested to begin with. And then like in second year, most of the courses were related to CS. And I got really interested in things like discrete structure for computer science or like other theory-based courses related to algorithms. So that's how I got interested. And I remember like in my second year itself, I requested my CS prof who taught us the algorithms course, if I could like do some sort of a project with him. So he got me a bit more involved in things like, I remember back in, yeah, not having good memory. Like, I mean, in the sense so much time has passed now. But like, uh, I think it was related to something around simplex algorithms. It was fun, and then I got more and more interested. And then like there were many topics that we covered. One of which was graph theory. I got more interested in that. And in my second year itself, I applied for some summer internships. Uh, I remember I applied for some internship, and then I also sat for internships to like in industry, and I got selected in Nutanix. And then like just before I was to go and start my internship in Nutanix, like by the end of second year, I also got an offer from Mitex. It was like a sort of a paid internship, but you do in Canada, and I got matched to some professor in University of Montreal, and that was like related to some project in graph theory. I Yeah, I thought like I mean I was getting more and more interested in graph theory and research in general. So I chose to went to Montreal, which was a very good region in hindsight. That was like my first exposure to doing some kind of research. I was there for the summer, and we I think like I worked on two very early some graph theory related projects. After I came back, then I was just like more and more involved. And in my fourth year again, like how it happens at BITS is that you can do a 6 month long internship in your final year at some industry place like Apple or again Nutanix or some other place. Uh, but I again like chose to prefer like to do some research and explore research more, and I applied a bunch of places, IIC Bangalore and Microsoft Research Bangalore, and thankfully I got a call from like some of these places. I gave some interviews. It was like a very quick sort of interview rounds, and I got matched to this researcher called I mean his name is Ravi Shankar Krishnaswamy. He did back then things around approximation algorithms and a bunch of other like theory related stuff. He was from CMU as well, by the way. So then I went there, did my undergrad thesis. That was an awesome experience. I would say that was like, the first full fledged like a very knee deep research experience for me, where I worked on two problems. And I mean, yeah, I mean, okay, to keep it short, but like that's how I slowly at after year, I got more and more interested in research in general and CS, exploring to begin with in those days more theoretical CS.
Awesome, awesome. Very, very exciting. Okay, great. So I guess like maybe walk us through a little bit about, sort of this paper that you've worked on, right? RL scaling laws, super duper exciting stuff. Maybe just tell us a little bit about kind of like first, like how you came up with the idea. So like Rishab Agarwal, who, used to be on the podcast, was at MSL and is now at Periodic Labs. Super exciting. He's like one of the co-authors, so I assume, you were working with him. There's apparently I think another Rishab on the paper. So you're also working with him. So you had quite the team. So maybe first let's just start off with the team. Like who is this team behind this research, and like what was the motivation? Who came up with the idea? How did you guys kind of first come up with the idea? And then I guess like slowly over time we can move more towards the technicals.
Yeah, very, very. It was a very interesting phase. So, uh, this idea, how it came was I was interning. So for like past couple of years, I was interning at Google, and like this time I decided I would intern at Meta, and I started internship with two people. One is Rohan Anil, who's also no longer at Meta now, and the other one was Rishabh Agarwal, who also left. So we started by exploring a lot of different things. We started like I think initially exploring adaptive compute for RL, um, because that's like some sort of work that I've done in past. And then like at the same time, Rishabh and David, who's also co-author on the paper, second last author, right? He They were working on something internal, and they like stuff that they were working on. It had like some sort of flavor to what this paper offers. So concretely speaking, like they were taking some algorithms and to some extent trying to find like how these two algorithms differ exactly. What is it that one offers and the other doesn't, and how is it better? So I was like very curious. Like they used to have this weekly post where they would post what they did the last week, their findings, the next steps, and I used to read it all. It was like a very thorough, detailed post. Like I remember, it used to take me like two hours or something just to be very thorough with the post that I read and understood everything. And then I posed like a lot of question in comments, and I would even message those people who were involved in that work. Uh, and so yeah, Rishabh saw that like I'm getting interested in like sort of analyzing these algorithms which are already existing, like nothing necessarily novel that we are proposing, but like understanding them better. How are they working? How are they contributing to RL? That's how it started. And then like Rishabh pitched this idea to me that why don't we analyze in a very principled way what is it that they bring to the table. There are so many algorithms out there. DAPO, WAPO, GRPO, GSPO, like every single day some new algorithm will come. That's how we pitch me. He said, every single day a new algorithm will come. Everybody will claim that they're the best. Well, of course, there could only be like single thing which is like better. So can we just have a very principled study about all these algorithms and do some sort of science of how to do RL? And that like resonated very with me. I mean, initially when he said it, it took me some time to sort of think through and like think about it. Is going to be really good. I was like, okay, it makes sense. Yeah, let's do it. Uh, and Lovesh had been involved in almost all my projects that I was doing at Meta. I had worked with briefly with Lovesh and interacted with him when he was back at Google DeepMind. He was a pre-doc there back in India, and I was interning back in India in past. So that's how I met him. So he was like a good friend, and someone who was already there, who knew who could help me more frequently on how to run stuff, how to find compute. He's pretty good at it. So that's how it started. So Lavish got also involved, and then uh, we discussed on how to move ahead. And we first thing we realized that it's a lot of work. We wanted to be very thorough. We wanted to run a lot of experiments. It would be nice to have a good strong team for it. So then Lavish stepped up, and then he was also like, yeah, man, let's do it. So we both decided that we'll just work together on it. Uh, and the other people, Rachit Bansal, Rishabh Tiwari, Sai Surya, these three are also my friends. Some of them I know from, again, Google DeepMind, they were pre-docs. So Sai Surya is another PhD student along, like, from working with Indrajit, so he's in the same year as me. They all were interning at Meta at the same time. And I used to discuss with them what I'm doing, like we just used to like, you will see some Rachit Bansal's paper and I'm a co-author in that because we used to discuss research with each other, what they're doing, what I'm doing. That's how we got involved, the rest of the authors. The last three authors, Indrajit, he's my advisor and I used to update him on what I'm doing and he used to give me feedback. That's how he was involved. And David and Rishabh, I already told you about, of course, like main folks. That's how it started. If yeah, I guess that answers. Yeah.
Yeah, awesome, awesome. Very, very, very helpful. Okay, so sort of continuing on, right? Like, you had built sort of this great team. You know, you were interning with Rishabh, who's obviously incredible. Walk us through a little bit of kind of like the early days of working on this research project. Like, kind of like what were some of like the pitfalls? What were some of the problems? Like, what were sort of like some of the moments where you were just like, is this even worth doing? You know, I think like in our podcast with Rishabh, we talked a lot about kind of research generally is not always going to lead to a NERP's best paper award. Like many times, it's just like a series of failures, and in many ways,
Yeah.
even failing is actually good because it gives you a lot of really valuable experience. Why don't you just like list all the failures for this paper and like kind of like what you learned from them, kind of how that pushed you?
Yeah, so I will tell like a few challenges that we faced initially, especially. Uh, so how we started it was we knew that is gonna be like a pretty. We aimed to have it very thorough and a large scale set of experiments. Now, in order to get started, one thing we wanted to make sure was that our setup was correct because we can't run all the experiments again. It's like so costly to run them, right? To even get those resources. So it took the main challenge I would say in this project initially for us was to just to find the right setup. And by that, what do I mean? There are a few things we needed. One, what model to work on. Second, what data to use for RL. Third, what data to use for SFT. And we wanted to make it like use as much open source stuff as possible because like it's good. People could try to at least partially reproduce, uh, and also easier to get approval to get like publication out if we use open source stuff. Uh, so we started by doing SFT first, and for that we took this data from Nemotron and Open Thoughts and bunch of other like open source SFT dataset thinking traces. Uh, we wanted in order to like iterate faster, we decided that we are going to have 12K length for our RL rollout, 12K for thinking and plus 2K for run, so there are around 14K tokens of rollout. Initially, the challenge was that if we started with this open sourced SFT dataset, the SFT model itself would start at a pretty high sequence length. Like it would start around at an average around like 9K or 8K, and it will grow till like 11K. We wanted to show a better growth. We thought that okay, this is not the right setup. We wanted to start with something much smaller, maybe 5K or something, and then grow over time because that is like we wanted to like how do we have a sanity check. It's not necessary to have the behavior that I just mentioned, but it's a good sanity check that is behaving somewhat like expected, right? So we spent a lot of time in analyzing, and we thought that there's like something wrong going on. We changed the model. The effect was same. We took subset of the SFT dataset that only had at most 12K tokens, including the prompt. Still didn't change. We did more amount of SFT, still didn't change. We're like, what is happening, man? uh, and then we had some insights onto like why is that behavior coming up? And I guess like the insights might be part of some other paper. So I will not go like too much deep into it because there's like that itself is like a research problem, I would say. But eventually, what we realized is that we needed to change the SVT dataset. So what we did was we took some part of it from open source thing and some part of it sort of a closed source thing, I would say, like, but it's basically like multi-shot prompted memory data. And that worked out. So now we had like initial generation length around 5K, and every other metric that we can sort of track, how is entropy going, how is grad norm behaving, how is everything else going, it was like according to what we would expect. And we were like, okay, fine, we are good with the framework. So that was like one big challenge. I would say this, yeah, initially that was one big challenge. The other big challenge came in terms of how do we even run so many experiments. Uh, it's not easy to get compute. Everybody wants it. Everybody wants to train these nice models, and internally, like more compute is always good for them to have. And we got like really lucky, I would say, because what happened is Meta just onboarded their GB200s, and they were still setting it up correctly for people to use, and there were like a bunch of reorgs and all that were going on. Probably you are aware of it, and in all that time, it it got us time that like nobody was using those GB200 at the same time. They were not set up enough for everybody to use, and me and Lavish especially because he's been here at Meta, he knows like how to set up these machines, set up the content environment, so on. Like he figured out like how to make use of them, and we were like, yeah, man, let's go. Like they were like, I remember initially there were I think 5,000 nodes or so that were brought, and then we were like, we bombarded like some 3,000 nodes. Like let's go, and we made like a very fast initial progress in this phase. And I remember, like, I was visiting India at some point when I was doing this intern. I'm not internship, but like did this work. And I used to work like during the daytime in India, and Lois used to work during the daytime in London, and it was like a constant thing going on. working throughout and just making sure that we make best use of this opportunity of having so much compute. That's how we got like bunch of our such large scale experiments, so many ablations. That was like the second challenge that we faced initially, but thankfully worked out. And then like soon enough, like people figured out how to use these GB200 because they saw our configs, lol.
Yeah.
And but thankfully in that time some other resources got free and then we pivoted. But yeah, those were I guess I would say like two weird challenges. Yeah.
Yeah, no, awesome. Yeah, I think that's a very helpful context. Okay, so like sort of switching gears a little bit. Let's say that you had to sort of summarize your paper, in maybe like 2 minutes to an audience that's technical and has a decent understanding of scaling laws and also like a decent understanding of RL. Maybe just sort of like outline, maybe as clearly as you can, kind of the impact. Like, what do you think is sort of like the groundbreaking achievement here? Like, why do you think it's so different than all the other scaling laws? And we have seen a lot of scaling law papers, especially recently, and a lot of RL papers. Maybe less on RL scaling law specifically. So maybe just tell us a little bit about kind of like if you had to summarize impact, what would you say is the impact? And then we can start to get more technical from there.
Right, yeah. I would try to give like a very concise summary. So if I had to say what is it that we present in the paper, the main takeaways. So RL is, as we all know, is becoming more and more important. Compute is growing. Uh, we want a principled way to scale it up. Now, this question is a very broad question of how we scale it up. Does it first of all scale up? Second, does it scale very predictably, in a stable fashion? How do we know that what RL algorithm to choose? Like today, I could have written a paper in which we just presented just the recipe and said, oh, it works better. But that is not like what we wanted to do. We wanted to present a framework through which people, even in future, if they want to build a new algorithm, they have a way to compare with the existing one, and they have a way to compare of exactly how is it better. And using the same framework, you can analyze a lot of different things that go in an RL algorithm or a lot of different design choices, and find out how does it really contribute. Is it like making the ultimate scaled up when you scale to a very large compute that performs better than asymptotic performance, or is it really just making it more efficient, faster to go to that asymptotic performance?
Mm-hmm.
So that was the first part, the framework. Now, once we have the framework, what do? We take whole bunch of different axes on which you can change the design choices of RL, and you compare them, and you take the best out of them, right? And then you combine them, and
Yeah.
that's what scale RL, the recipe that we also give in this paper. That's what scale RL is.
Mm-hmm.
And we make sure that it's like a pretty robust, pretty good recipe. In terms that once you have all these best things combined, if you leave one out, is it still the best? Like, is it worse than having this involved? And true. So scale RL is like robustly good, uh, and we scale it up across different axes. We expect a nice, a stable algorithm to perform better when we increase generation length. Does it do? Does it do like even now? Answer is yes. Does it do it predictably? Yeah. Similarly, like we expect it to do better if we increase batch size. Again, like whatever we expect is happening and is happening predictably, so all good.
Yeah.
We expect it to be better like when we increase the model scale. Again, so all expect things. So that's like at a high level what we present in the paper.
Awesome. Okay. All right. Now let's get into the juicy details of this very 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 juicy sandwich that is this paper. All right. So, let's go ahead and let's get cracking. So, first things first, right? Like I think generally like the paradigm, like you sort of present, I think sort of figure one front and center in the paper. You're sort of talking about like the scale RL 8B done, scale RL 117B X16 MOE. You show like the AME 24 scaling RL compute. So maybe just tell us a little bit about like, from a paper perspective, there's often kind of a design choice that comes in as to like what is the first figure you want to put front and center. And I'm nearly positive that there's probably a reason why you guys put this front and center. There's also probably a reason why on page 3 you guys have a diagram where you sort of show GPU hours times 10 to the third log scale versus pass rate log scale, and you basically are comparing like scale RL, minimax, magistral, Quen 2.5, DeepSeek, so on and so forth. And I mean basically what you end up seeing here is right scale RL sort of like I guess quote unquote outperforms like I guess like as GPU hours continues to increase, pass rate also increases. So maybe let's start with the first one. So talk to us a little bit about this diagram, kind of like what was the motivation behind having this diagram front and center. Then number 2, let's talk a little bit about the second diagram of like why scale RL being higher, like what does that actually mean? like from a technical perspective, like what does it actually mean for you to have a higher pass rate? And then we can keep going deeper.
Yeah, yeah, good question actually. So true, yeah. First paper, my first image in the paper, that's like pretty important, as you would all, you all know. Uh, how we decide on it? We thought, what is it that we want the reader, if they just glance at the first page, what
Sure.
is it that we want them to take away? And we want them to take away one, that RL is, if RL training is predictable, they can follow a predictable curve. You can fit a curve and you can tell how it's going to perform if you just extrapolate without actually running the experiment.
Yeah.
That's one thing. And second thing we wanted to say is that it it works across things. Like it's not that, like, for example, the first image that we had actually put only had the 8B model scale. But then we thought, okay, what if people interpret that, oh, saturation is there like after you reach 16K GPUs, so you can't scale more or something like that, or like whatever 50K GPUs. And we wanted to say no. I mean, there are many different ways to scale it up. Batch size was one, but we want to say that like if you have a better model, you can get like better performance. So we put a much larger MOE model scout up there to also show that it generalizes not just to one model but also to MOEs. It increases performance in the way that you would expect it to be, at the same time still being very predictable. There are two figures. The left one is on the validation set, which is what we use to fit the curves and do the extrapolation. On the right side, we have the EM24 plots, and that is to show that you the kind of improvement that you're getting, it also translates to downstream task if you do it right. So that was like sort of the main takeaway. We thought that there is this recipe, so it's a good recipe, and the framework we introduce how to fit a scaling curve and extrapolate it. That's why the first figure. Yeah.
Awesome. Okay, let's get a little bit deeper. So, another thing that we sort of talk about is like whether scaling up alongside, generation length, model size, batch size gives you expected gains, right? And you sort of like show in the paper that it does. You also show that like now you can sort of analyze how exactly they improve performance. I think you talk about this concept that, like for like a smaller like BSZ and like gen length, like that might seem better initially, but the larger ones overtake eventually. This brings us to sort of like figures 9 and 10. Here you sort of have four different figures that you're talking about. So okay, so maybe let's try to like recontextualize this. Like, what do you think is sort of the impact here? Like, do you think that anybody has like studied this before, this specific phenomenon, these graphs? How do you think this sort of relates to like the rest of the paper?
Like one thing we wanted to show up was that, uh, so what's the benefit of having this fitted curves? It is that it can tell you how the performance will be eventually. And so what's one interesting thing that can come out of it? One interesting thing that can come out of it is that what if something which seems not so good right now may outperform in like finally, right? That was an interesting thing, and we saw that at a couple of important places. Like, I mean, as you said, the batch size being one. It outperforms eventually in terms of just asymptotic performance, so making your RL algorithm more scalable. So it's pretty important. Uh, and can you repeat your question again? Was there something else that you asked?
Yeah. So I guess like I mean, like there's a few different parts here. So in your diagram, right, you have a few different parts. You basically show that you can like analyze how exactly it improves with performance. So for instance, like basically you can show that like as you scale up, alongside generation length, model size, batch size ends up giving you expected gains, right? And I think you had four different figures. Like one is sort of figure 9 where you're sort of showing scaling RL generation length. Another one is figure 10 where you're sort of showing scaling RL batch size. I think in like the bottom right of these figures, we see that basically like at the very beginning, scale RL BS 2048 sort of starts very low, but towards the end they start to converge, if I'm not mistaken, right? Or it seems like it like scale RL BS 2048 ends up sort of outperforming all the other ones. So I guess maybe we can start with this like intuitively, like yes, authors or I guess like readers can look at these diagrams, but they might not understand why it is the case that the green line is separated, right? Sort of looking at like one of the diagrams, you're plotting GPU hours times 10 to the third versus pass rate, and we see that like when you're sort of comparing a bunch of different points where one might be, for instance, I think it's you basically have like scale RL BS 768 and BS 512, and those are very tightly knit, like they're very close to each other, and then a little bit separated away is like scale RL BS 2048. Maybe tell us a little bit about like why that is. Like, is there a reason why like 512,
Okay,
768 are so
okay,
close?
that's a very good question. So
Yeah.
first of all, uh, it's as you rightly noted, like it's important to know that 2048 batch size or basically like higher batch size run, they start off a little lower in performance
Yeah.
initially, and
Exactly.
that's mainly because it's like larger batch size, so each gradient step takes a lot of time,
Yeah.
and initially like you can have a lot of improvement by if you have just like decent gradients. When I say decent gradients, isn't like it provides decent information, it's not too noisy, uh, but if you have a lot of gradient updates,
Sure.
but eventually once you have scaled up, if you keep having some sort of noisy gradients, they're only going to take you so far.
Sure.
And so larger patch size like helps you have much better signal,
Sure.
and it takes you at a much better performance.
Sure.
So that's how it like eventually takes over.
Sure.
I would say somewhat similar for uh, generation length. That longer generation length, it's like slow initially because the rollout time is quite high. So it takes a lot of time to do 32,000 tokens rollout compared to say 12,000. Um, Almost like three times, right? So
Yeah.
there again, like initially, the gradient updates were much faster with the 12K one. But once you have trained for enough long, you can only solve problems that are only like so much hard, like not
Yep.
beyond a certain hardness.
Yep.
And longer generation length helps you think longer. So even intuitively, one would expect that eventually it should outperform, because if I just let it like train till infinite time, that's what
Sure.
we expect and that's what we show.
Sure.
So that's like sort of making sense that way as well.
Sure.
uh, as to like the specific reason of why there's not so much gap between 512 and 768, but a bit more of a gap between 768 and
Yeah.
248 is, first, there's not so much gap between the batch size of 512 and 768
Yeah. Yeah. Yeah.
compared
Of course. Of course. Of
to
course.
it. That's
Yeah.
one
Yeah.
thing.
Yeah.
Secondly, also like I mean, when we were running these experiments, most of the large scale experiments were like more last moment, and we wanted to get them done faster. We wanted to
Sure.
have a 100K run,
Sure.
so we
Sure.
ran it on uh, more number of machines as well.
Sure.
Uh, that may have impacted a little bit. Uh, and the third is when you have a larger batch size, what happens is uh, your generation length grows faster per step.
Sure.
So if your generation length at a given step is larger for a given run compared to the run, it will also amount to the time that you are taking, because now you will also be spending more time in the rollouts.
Yep.
So a couple of these factors like together, they just made the 24/8 one a bit more like it looks a bit more slower initially. But I would say the following: like, what's the main takeaway is that tomorrow, if you just uh, implement this work on your setup, on your infra or whatever, you might see a little bit different, that maybe they are not like it's not as low in comparison. It may start rising up initially a bit faster than it is currently in the paper. But that's not the main takeaway. The main takeaway is that it is quite possible that will start off being like having smaller performance or
Mm-hmm.
less performance, but
Mm-hmm.
eventually for sure it will go up,
Mm-hmm.
and that is extremely important, because what do we even mean when we say that we want to scaling up RL? We want to scale up and we want to get as good a performance as one can get when we scale up to a lot of compute. So we definitely want something which has a higher asymptotic ceiling,
Mm-hmm.
reaches a better value.
Yep.
That
Yep.
is
Yep.
like
Yep.
first thing that one should keep in mind, right?
Yep, 100%. Awesome. Okay, let's get into some sort of like the discussion conclusion. I think this is oftentimes like the most interesting thing. I think like, it is a great paper and people can sort of read up on like the math formulas and probably ask in questions, but I think it's always very exciting to talk about like why there were certain decisions that were made, right? So there's this decision that was made about, like the op policy algorithm, loss function model precision. They are the most important decisions from the ablations, right? And I think this is something that you mentioned pretty much verbatim in the paper. I think you also say, and I'm quoting here, like each of the other decisions does not have a large individual effect, but as we see from the leave one out experiments, they still do have some cumulative impact in terms of efficiency when all combined. Okay, so now the question to ask here, right, is why is it that off policy algorithm, loss function, and model precision are the most important decisions?
Yeah, pretty good question. So, I would rather like see the. I will just rather just like modify the question to be, what are the most important things that one should keep in mind among all the things that we analyze?
Sure,
What is it that we found the most important?
sure,
One is the loss type. Why loss type? Well, first, if we look at the baseline algorithm that we started with, which is like in the sort of forward, I call it forward ablations, which is like around 3.5 to 4K GPU hour scale. There we started with a sort of like a DAPO implementation, a very basic GRPO DAPO sort of
Sure, sure,
baseline, and
sure,
we only change one thing at a time. And there, a few things that changed the asymptotic performance by quite large amount was one, the loss type, and second, uh, using FA32 at LM head, or in other words, like if you can somehow make the trainer and generated logis mismatch, uh, somehow like you resolve them. I mean, we use FA32. That's one way to resolve it,
sure,
and there are many other ways to resolve there that are published in the committee. So
sure.
they like consider thinking lab blog, for example, like they have some other way. So so that's how we said that these are two very important. It affects the stability itself, and how much are you uh, sensitive to hyperparameters. For example, loss type, we show it even in appendix that if you take CISPO, you change your epsilon max from 4 to 5 to 8 or 3 or whatever, it doesn't
Sure,
change as much, like
sure,
pretty
sure, sure.
robust. But if you change your epsilon max of the DAPO from 0.24 to 5 to 6 to 0.24 to, like, you just change even by my slight amount 0.01, it affects the asymptotic ceiling that it can reach altogether.
Yep,
That's a very, very large effect, right?
yep,
So that is why the loss type is important. Second, as I said, like FP32, this has been recently coming into more and more notice by a lot of other folks as well. As
yep,
I said, like Lab Machine Blog is like one popular example, and there
yep.
are more people who are saying that the train, like infra, there are like a lot of challenges in infra in RL, and one of them people is noticing is that there's a mismatch between the trainer and generator because they use different kernels to be efficient. One uses training kernels, and one uses like inference kernels. So this makes the computation a bit different. So even if you have same model, your final probabilities could be different. As a result of which, when you take the ratio of probabilities, like that which you do in off policy or like slightly off policy algorithms to do some important sampling, that ratio gets screwed up. And one can also think of this in the certain way, right? Since CISPO is less uh, uh, is like less sensitive to the choice of epsilon. That's why even without fixing the FP32, it was performing good. It was
Sure,
less sensitive.
sure, sure, sure.
So when you take DAPO and you do the FP32 precision fix, then then like it performed pretty good.
Right.
So that's why like these two like pretty much affects very basic building blocks of RL algorithms, and we say they are very important. And about the off policy thing, mainly because I would say that it makes it very, very efficient. If you look at the first figure among those in the forward application, it's like you take your just the classic PPO one step of policy, classic PPO eight step of policy, and then you take the pipeline RL. It's just like very, very much more efficient.
Mm-hmm.
And I can also like maybe just say very briefly why is it so? Because the way pipeline RL works is that this generator, there a trainer.
Yep,
The moment generator has generated some rollouts,
yep,
it doesn't wait. It just says that take these rollouts,
yep,
do your batch. It is
yep,
fine,
yep, yep, yep,
and I'll just keep generating more on whatever current copy that I have.
yep,
At the same time, trainer, whenever it has taken a gradient step, it won't wait. It'll just give the model updated model weights to the generator and say that
yep,
here are the new updates, new model weight, and continue generating using the stale KV cache. It's fine. You can just use a stale KV cache, but continue generating using this model onwards.
mm-hmm.
There is no waiting for each other like in a classic PPO of policy algorithm,
Of
and
course.
that's one of the main reasons why it's much more efficient.
Awesome. Okay. All right. We're gonna move to more rapid fire for what we're about to hit. So as probably the audience can smell, this gets more and more intense as we continue. All right. Let's look at generalization. So you basically talk about how in the paper like you sort of have this question of like how well the LM would generalize from the training distribution to held out test sets. I think you guys say that it's like outside the scope of your work, but you do observe, and I'm quoting here, a correlation between in distribution validation and downstream generalization performance. But then you also say that there's some algorithmic choices that seem to help generalization more, including like larger batch size, reducing truncations, longer generation lengths, larger model scale. Okay, so here once again, same question, except much faster here. Like, why these? Like why these algorithmic choices? Also, like we you do say that like full characterization of generalizations beyond the scope of the work. When you say full characterization of generalization, like what do you mean by full characterization specifically? Like what are like kind of the remaining parts that are specifically are out of scope, and what specifically is within scope? Maybe just clarify a little bit about that.
Yeah, again, very, very good question. So true, the generalization was a bit out of scope, and I will speak more about that soon. First, answering about what affects. So if you look at the downstream performance plot of ME24 of the different batch sizes, you will notice that the 768 one, it goes up, and I don't have the plot in front of me, but like
Yeah.
at the end, at the last maybe 4K GPU hours or something, or maybe even 6K GPU hours,
Yeah.
it's like almost stagnated. Like, it's going up, and then like it's now it's stagnated. It's not improving further.
Right.
Although the larger batch size, like it keeps going on, and at least till the point we plotted, there was not much of a stagnation that we saw.
Right.
Whether larger batch size or larger model size or larger generation size.
Right.
Now, why is that happening? Is the way I look at it is, see, uh, one, of course, the training is better with larger batch size, which is showing even on validation curve. And it's not just better, like one should not look at it that the going from a validation accuracy of asymptotic accuracy of, let's say, 0.58 to 0.60 is less good than going from 0.60 to 0.62. Like the more higher you go, it's very becomes more and more tough to improve.
Sure.
And that starts like showing up truly in the downstream as well. So that's why,
Sure.
even though you would say that, oh, validation curve, well, yeah, 2048 looks better, but only so much better. But no, it actually has a lot of effect on how overall, like how good it is.
Sure.
So yeah, just like better training with these larger scale axes
Sure.
and getting reflected in the downstream task.
Sure.
Like larger generation length, how I would think is that AME is a tough problem, and you would expect that at large generation length
Yeah.
should do better. That's what's
Yeah.
happening.
Yeah.
Right?
Okay.
So that's what is happening. And about the characterization, I would say that it's one main thing that determines downstream performance is the data itself. You can train on some very different data, and then you will not see any downstream, like, or not much downstream effect. But the more aligned the data is, obviously it makes sense. But also the more diverse in terms of how easy, medium, hard problems are, or those kind of stuff. Like those are the, I would say, yeah, data is like one important perspective which affects generalization.
Mm-hmm. Okay, awesome. All right, we'll do one more specifically related to this paper, and then we'll get into more general RL stuff. Okay, so let's talk a little bit about future work. So, you guys talk a little bit about how in the paper, right? Like the natural next step is to drive predictive scaling laws for RL across pre-training compute, model size, and RL training data. You talk about how like potentially some of the future work could include things like axes of RL compute scaling, like incorporating structured or dense rewards, which and some other researchers did, and more compute intensive generative verifiers. Okay, so there's a lot of different areas of future work. This is like a very loaded, like RL scaling laws is a quite massive thing, and I'm expecting a lot of papers to be generated in the next year. They'll be doing something very similar to this paper. So
Yeah.
how about this? Why don't you say like if one day you went into a time capsule and then you woke up and 1 year has passed, and in that 1 year a bunch of people like 100 200 different researchers created one-off branches upon this paper. So like they made a slight small improvement or maybe medium-sized improvement on the paper, so that way they could get it accepted at iClear or something like that, and get some n% benefit on some graph. Out of all of these advancements of ways that people could potentially improve your paper, which one would you be most proud of?
I would be most proud of things which explore things beyond, like, or I would say, like, in a more holistic way
Yeah.
of how to spend compute. See, the way I think of doing RL training is that there's some black box.
Sure.
You have input, which is a model, and some whatever data. I mean, you can choose data, whatever, but there's some input which takes model and a bunch of other things which you can input. The model is constantly, say, I give you the model, and I will give you the compute. These are two things that I give you. You are the black box. You do something about it, and you come back to me and you say that, hey, I used all this compute, and this is the best model I can perform. There's a lot of things that can go in that black box. It could be, like as I said, the future work could
Yeah.
include having better verifiers which are themselves like thinking models.
Sure.
Just think about it,
Sure.
and like maybe how uh, they can make use of dense rewards. So it could be possible tomorrow that we are giving sort of a text feedback to the model on what part of it is good, what not. all of these different ways to spend compute when doing RL has some trade-off.
Sure.
Has some trade-off as in like if you give dense feedback, the dense part will require some compute to be spent in
Yep,
order to
yep,
be
yep,
dense.
yep, yep.
Similar, like much better feedback in terms of like if there are like thinking models giving the feedback on problems which don't have a ground truth available.
Yep.
Uh, Again, like that's some amount of compute that we are talking about, or any other access, I would say.
Mm-hmm.
What, like, how do all these, when we take, there are so many different directions that one can
Yeah.
use to train this model,
Yeah.
which what sort of best combination of them come out to be most effective,
Yeah.
and how? And I would be like very like, and there are many different things that can come out of it. For example, like if you give dense feedback, there could be a large game, not just because of dense feedback, but like for example, like there's this recent work which say that there's only like order of one bits which you receive, and maybe now you're receiving much higher number of bits of feedback, and so your training is much more efficient. You It leads to self improvement because now you can put two and two together from your train dynamics and then solve next time problem that you were not able to ever solve it. There are so many nice things that can come out of trying different ways to spend the compute, and I think like our framework helps them analyze of what is better given a fixed compute, how is it better exactly, and where do you eventually reach.
Mm-hmm. Awesome. Do you think, okay, so now we can sort of move to a question that's like semi related to your paper and semi related to RL in general. In all of these possible advancements people can make, like, what do you think the bottleneck is? Like, is there any like current bottleneck of like there's this particular factor that's stopping us from improving, RL scaling at a certain level? Like, there are many ways to improve this paper, right? Like we sort of talked about in future work. Obviously there is going to be some sort of optimal configuration, like you sort of alluded to, where like you can sort of tune a lot of different aspects, make all these small improvements, join them all together, and build something better. And maybe there will be something better. That sort of things from first principles. Like, what do you think the limitations will be? Like, what do you think the obstacles will be in doing that? Do you think that there is any sort of other research problem that's related? Like for instance, verifiers is a huge problem, right? This is something that like Rishab talked about on the podcast, but is like probably one of the hardest problems to solve. And so like the ability to create a good verifier might be one form of a bottleneck. What do you think are some of the other forms of bottlenecks that you've observed?
I think like one immediate bottleneck that I see, like if I had to answer right
Yeah.
now, what's one bottleneck that I see, especially in open source community, is the infra.
Yeah.
I feel that there's not a lot of good infra.
Very
Tomorrow,
true.
if
Very
I ask
true.
someone, yeah, if
Yes.
I just ask someone, can you just reproduce this work? First thing they'll be like, is it something that works pretty good? Distributed computing and then distributed training, and then
Yeah.
it has good infra, supports pipeline RL, bunch of other things. That's one of the main thing, and it's just infra is just the need of infra is just growing in general because people are trying to train using like different environments, and again environments require a good infra. Uh, so that is like one immediate thing. As you said, the second thing is um, a good verifier, and the
Right.
third thing I would say is uh, I would say it would be nice like if we can have better off policy training methods, uh, because I'm just thinking on the go. I'm just thinking like if there are off policy algorithms which perform pretty good, then what it means is that you can scale up because you can just generate a lot of data
Yep.
in parallel,
Yep.
make better
Yep.
use of compute,
Yep.
and uh, then later just like do training
Yep.
when like just do it training. So the more off policy you can get, the more efficient you can get.
Yep.
But this of course a trade off. Too much of policy is not relevant to the model and so on.
Yeah.
So some more improvements over there would be, yeah, nice.
Yeah, awesome. Okay, let's move a little bit more off the theory slash like super duper technical details, and now let's talk a little bit about like tomorrow you're magically at a farming company, and the farming company wants to create some sort of RL algorithm just because they want to do some enterprise RL thing because everybody and their mom these days is doing RL for enterprises and RL as a service and RL environments. I'm not going to name specific startups, but let's just say that many startups are doing this. And so you're at this farming company and you're working on building this RL environment. And you're building, and you need to consider scaling. Like, what do you think an enterprise, right? That's like maybe not super researchy, maybe more on the applied AI side, maybe more of a consumer of RL or somebody that's maybe using other existing RL techniques or RL libraries. What do you think they should know from this paper? Like what do you think are sort of the key, contributions on the applied side that you think that large companies, large enterprises that are looking to explore RL should know?
Yeah, good question. let me think. Like, I mean, one thing is that if you're doing, if you're using your um like RL for science, right? I mean,
Sure.
then one thing you need is a, which is not really covered in this work, but I
Sure.
would still recommend is uh, having a very good base model.
Mm-hmm.
RL, right, at least right now, how it is that you don't start with some okay model and you just like evolve. You start with some decent good model which has like good priors, and then you like make it much better.
Yeah.
So having a good model which has the capacity to be as good as RL can make it go. That is important to have a good just base, a good base model in terms of capacity and the price it has. That's important. Second, like from this paper, what I would recommend is having yeah, I think like having this principled way of comparing on what to use. Uh, when you use, like for them, they might be using some different algorithms, which is fine. But every time that they think of using an algorithm, one will always wonder, is this right? Is this the right tool that I'm using? Is it the right way that I'm scaling up? Is this the right design choice that I'm making? And to use this scientific framework or like way to compare two different methods, I would say that is like one good takeaway, irrespective of whether one is doing RL or not. Just like how to compare two different methods in a methodological way.
Sure.
Yeah, science of doing it is what I would say is one takeaway.
Sure. Awesome. Okay. And then let's get even broader. So RL is one paradigm. There's a lot of other different things that are going on right now. I mean, obviously RL is big. Scaling laws are big. There's also the whole other area of our favorite word in Silicon Valley, agents. And then this is where we get into multimodal agents. This is where we get into web agents. This is where we get into video agents, so on and so forth. So maybe it's sort of zooming out, right? Like just in the whole whatever you want to call it, AI, whatever AI means these days, which really means like literally everything, because technically everything is AI now. Like how do you sort of like what are you most excited about? So let's like maybe pretend RL and scaling laws don't exist. And so you have
Yeah.
to recontextualize what you're excited about without related to RL and scaling laws. Like what are you
Right.
excited
I'm
about?
I'm most excited about what deep learning can do for science in general, outside
Yeah.
just math code and language and text.
Yeah.
The model could be it, and I think like uh, the startup that periodic lab
Yeah.
startup that Prishant went to. That's like I'm pretty excited about what are they cooking exactly, because it
Yeah.
seems that they're doing something more for science in general,
They are.
having some physical labs out there and then doing some experiments. Seems very cool, man.
Yeah.
There is so much that is possible kind of gains. Like, I mean, we have seen DeepMind give back to community, to science in some
Indeed.
very unique ways and
Yep.
different domains. We have seen it making some very good progress in terms of like protein structures, right? And then
Right.
like
Right. Right.
detecting some novel ways on how uh, to make a chess move and like a lot of different things, like just not related to the typical computer science things that people do.
Sure. Sure.
There's so much more out there. What can you do in astronomy? What can you do in just general day-to-day life
Yeah.
things and weather forecast? I mean, okay, I don't know, like I'm just speaking random
Yeah.
things at this
Yeah.
point, but like in general, how to use deep learning for things more broadly in
Sure.
science and for other domains like that is
Sure.
what I would be most interested in. I'm pretty sure that people are starting to tap into it.
They
I
are.
mean, as you said that there are like these hundreds of startups coming up, and each of the
Indeed.
startup is just saying, okay, I'm going to use deep learning and apply there. That's like this startup,
Yeah.
right? I
Yeah.
mean, it's fine. I mean, that's an important problem. It's nice. It's niche. I hope it works out for them. And so it's an interesting phase. I would say we are in a very interesting time. I'm pretty lucky to be alive and see all this transition happening at in our lifetime. It's like a
Yeah.
very excited in general about what deep learning is going to offer to the community as a whole.
Yeah, yeah, awesome. Okay, so yeah, I think we're pretty much close to time. So maybe we'll end with like one question here. So what are you excited about next? So we have this wonderful RL scaling paper that I think is going to do quite well. Let's hope. I mean, the conference review process is a bit interesting these days. So yeah, maybe that's not the best benchmark, right? Like maybe that should not be our verifier. You're given I've seen some 5.5 5.5 5s get rejected. Anyways, okay. So, like, what does success look to you? Look like to you? Where do you want to grow to in the future? And is there anything you want to tell the audience? Like, how should they? Do you want more collaborators? Should they reach out to you via email? Like, how can we be supportive?
Yeah. Thanks for that question. I mean, your support is just yeah. Like if you have any feedback, if you feel like we're doing good work, if you're using it, just give us a shoot out that like a shout out, and that would be like great. And um, what I'm most excited about next. Uh, this paper, yeah, it's good. The next thing there are a lot of different problems that I'm thinking of, right? So like the sign of how to do SFT is another question. How
Sure.
to do post training in general, because post training is becoming a more and more wider regime now.
Sure.
It just doesn't involve SFT and RL, but like in
Sure.
general, you have like agents and more stuff coming into use. Um, I think like post training in general, like and I would say self-evolving models is where I'm thinking about. I definitely feel the two, three things that we discussed in this podcast about having dense feedback and making things scale up even more can probably enable that.
Yeah.
There are many different ways to approach it, and yeah, currently like these days I'm thinking about what are the ways in which you can just really shift this asymptotic performance by quite a large margin, like or have more make RL give even more gains like in terms of number of bits. That's like sort of in shorter term what I'm looking at. What success means to me is to truly fall in love at a very broad area, in a very broad area, which seems to be happening of making things scalable and efficient. That's what I've been working for the past 2 to 3 years, and especially the post-training regime is just going in more and more in that direction, and I'm getting more and more interested. In fact, we submitted a iClear workshop proposal as well on scaling up post-training for LLMs.
Of
So
course.
again, like everything is sort of getting aligned in that direction. So I'm just hoping that I get so much knee deep and or neck deep in this, um, that I just understand it so thoroughly. I understand the science behind how it works, and intuitions come like once you are quite a bit into something, your intuitions become stronger,
Right.
and I hope to like make these nice applications of deep learning on how to do this training in the most efficient and scalable way, such that we train models which are really useful in making the lives of people better, and more than just code and math, but in general as well. To begin with, those are like the starting pivots, but eventually diverge to as a science like RL as a field. What can it do?
Mhm. Awesome. All right. Well, without further ado, we have one of the co-lead authors of the wonderful Scaling RL paper. Thank you so much for coming on, Devvrit.
Thank you so much for having me.